Okay, so this problem is a weak acid example problem, and it reads, what is the equilibrium pH of 5 times 10 to the negative 4th molar solution of boric acid, which is BOH3, in water? The Ka of boric acid is 10 to the minus 9.15. So we ask ourselves, is this a strong acid problem or a weak acid problem? Boric acid is not a strong acid, it's a weak acid. And so we know we're going to have to start writing our equations out. We're either going to have 3 or 4 equations. Let's start writing out the equations. First we write the reactions that we're dealing with. We always have H2O goes to H plus OH minus. Our other reaction is for boric acid. This reaction is technically BOH3 goes to H plus BOH4 minus, and in order to make this work, there needs to be a water on this side. We'll see the water, whenever we have water on either side of the equation, its activity is just going to be 1, and so it's not going to factor into our equilibrium expressions, as we'll see. So first we write our equilibrium expression for water. Kw equals H plus OH minus, which equals 10 to the minus 14th. And then we have Ka. We're going to have BOH4 minus times H plus. This activity of water is just 1, so we're left with BOH3. Now we're going to write our mass balance equation. We have 5 times 10 to the negative 4th molar solution of boric acid. What that means is, as some of this boric acid goes to the base, the total amount, 5 times 10 to the negative 4th moles per liter, since 1 mole of this goes to 1 mole of this, the sum of these two species has to equal the concentration, the molarity in the original solution given. So BOH3 plus BOH4 minus has to equal 5 times 10 to the negative 4th. And then we write our charge balance. We have on the right, we have in our 2 equations up here, our 2 chemical reactions, we have H plus as our positively charged species, and we have OH minus and BOH4 minus as our negatively charged species. So we have H plus equals OH minus plus BOH4 minus. So those are our 4 equations. We have this guy, this guy, this guy, and this guy. We have 4 unknowns, H plus, OH minus, BOH4 minus, BOH3. So we should be able to solve this. Let's move this over here. So. Okay, so now we are going to make the assumption that since we have an acid in water, that our resulting pH is going to be acidic. When we have an acidic solution, we can assume that H plus concentration is going to be much greater than our OH minus concentration. These 2 concentrations move inversely with each other on a log scale. So if we have, say, a pH of 6, we're going to have 100 times more H plus ions in solution than OH minus. because 6 is 2 orders of magnitude greater than 10 times the negative 6 is 2 orders of magnitude greater than 10 times 10 to the negative 8th, which is what the concentration of OH minus would be. So when we make that assumption, we can go back to our Ka expression right here, and we're going to actually first we're going to go to this guy right here, and we're going to say since H plus is so much greater than OH minus, this is going to basically go away, and so we just wind up with H plus equals BOH 4 minus. If we start rewriting our Ka expression, Ka equals, we're going to replace BOH 4 minus with H plus, so we have H plus on the top times another H plus, so H plus squared. On the bottom we have BOH3. We'd like to be able to express that in terms of the H plus concentration as well. And so if we go to this equation right here, let's write that up here. We have BOH3 plus BOH4 minus, which we said was equal to H plus, equals 5 times 10 to the negative 4th, and thus BOH3 equals 5 times 10 to the negative 4th minus our H plus concentration. So now we can replace that in the denominator, 5 times 10 to the negative 4th minus H plus. Ka we said was equal to 10 to the minus 9.15. And so now we can solve for the H plus concentration. Easiest way to do this is just with guess and check on your calculator, although you could rewrite this in the quadratic equation form. I get H plus concentration equals 5.91 times 10 to the negative 7th. Negative log of the H plus concentration equals our pH, which is 6.23. So that answers our question, what is our equilibrium pH of 5 times 10 to the negative 4th molar solution of boric acid in water? Here we have a pH. We should always check our assumptions. We assumed our H plus concentration was much greater than our OH minus concentration. If we can now go back and check that assumption. If we go back to our Kw expression, Kw equals 10 to the minus 14th, which should equal our H plus concentration, which we said was 5.91 times 10 to the negative 7th times our OH minus concentration. We solve for OH minus, and we get that it's 1.69 times 10 to the negative 8th. What's our error here? If we say 1.69 times, we assumed OH minus was basically 0, so if we say 1.69 times 10 to the negative 8th over our H plus concentration, 5.91 times 10 to the minus 7th, we see that there's actually 0.03, or there's roughly about 3% as many OH minus ions as there are H plus ions, and we assume there was 0. So roughly, we've got a roughly 3% error going on here. It's not exactly that, but so that's how we do it. We just assume if we're adding acid, if we have an acid, our pH is going to be less than 7. We're going to assume our H plus concentration is much greater. That helps us solve these equations. We could solve them all simultaneously without making that assumption, and we should get the same answer, but it's slightly more difficult. Again, if you do make the assumption, you should check it at the end. Make sure that your errors are fairly small, And that's it.